Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing, and this is density of state function part 2 as the lecture. We will start from where we had stopped in our earlier lecture, and that is the Fermi potential and the Fermi energy of an electron. So if you plot, therefore, just refresh your memories by your previous lecture, that if you plot f of E versus E energy here, this is f of E, then at Fermi level at 300 Kelvin, let me just first talk about this dotted curve and then we will go one by one. If you look at the dotted curve, then it makes it clear energy below Fermi level or low values of energy below Fermi level will always have probability of finding electron is 1, and therefore all the states are filled up. Whereas if you look at the energy beyond EF or more larger than EF, then you do have the probability of finding there is 0, and therefore it is a flat curve which you see here, right. Now let us increase the temperature to a higher value. So T equals to T1 and then T2 and so on and so forth. This is for T equals to T1, this curve, right, and this is for T equals to T2. Now as you can see, as T increases, the temperature increases. Let us go step by step. As the temperature increases, more and more electrons will be moving from a lower energy state to a higher energy state. What does it actually mean? It means that the places or the energy which it leaves becomes empty, and where the electron occupies, it now is become populated. So if you look at this T equals to T1, then you see that the probability has actually fallen down, right. Probability has fallen down from 1. Why? Because not all the states below EF are now filled. Some of the states, the electrons have left the states and gone to a higher energy level beyond EF, correct, and that is the reason we define that at T equals to T1 this many number of energy states will be empty and exactly same number of states will be filled up above EF. So that symmetricity has to be maintained, that the number of states filling up here is exactly equals to the number of states which is getting emptied below EF. Now if you take T equals to T2, which is more than T1, more energy states will be empty, and therefore you see this has shifted to the left, the probability, and therefore this is shifted to the right also here, which means that more now energy states will be occupied. So this is a perfectly symmetrical Fermi-Dirac function. This is known as a Fermi-Dirac function which you see, this is on the right hand side, and that is the reason you will have now Fe not only dependent on the energy state, but will also depend upon the temperature. Higher the temperature, lesser will be the probability of finding electron below Fermi level, and higher the temperature, more will be the probability of finding the electron beyond Fermi level. So again, let me compound this with a numerical example. So the question is, calculate the probability that an energy state above EF is occupied by an electron, and we assume that T equals to 300 Kelvin. So this is the first part of the question. The second part of the question is, determine the probability that energy level 3 kT above Fermi level is occupied by an electron. So there are two problem statement. The probability the energy state is occupied by an electron, calculate the probability. So what we do is f of E is equals to 1 by this formula which we have seen. The question asks that 3 kT above Fermi level, which means that E minus EF will be equals to 3 kT, right, and if you solve it, this will be exponential 3 and you will get some value as 4.74, which means that at 300 Kelvin approximately 5% of energy states above Fermi level will always be occupied. So this is one of the methodology by which at the same temperature, if you want to find out the probability of finding electron beyond this can be found out, right, this can be done. Now let us go one by one. Now if you this is a graph or this is a plot showing the Fermi energy on the y axis and energy on the x axis for both electrons and holes. So the dotted curve is for holes and the full curve or the dashed line is for electrons, this one for electrons, right. By the way, this profile is for temperature more than 300 Kelvin, right. That is the reason you see these are not perfectly square shaped, but they are a bit the regular change in the value of the Fermi potential. Now if you see this plot, it tells me that the dotted one is 1 minus f of E will be just antisymmetrical of f of E. So if f of E is given by this formula, 1 minus f of E, you can understand, no, because if this is 1 minus f of E, whenever f of E goes to 1, this whole function goes to 0, and whenever f of E goes to 0, this whole function goes to 1, and that is what is happening. You see, when this is 1, this goes to 0, and when this goes to 0, this goes to 1. So this is just keep in your mind at this stage, do not worry about the holes at this stage, but just keep in your mind that the 1 minus Fe will be always antisymmetrical sort of with respect to F of E, which is the Fermi level potential of electron. Okay. If you therefore, now let us take both electrons and hole concentration into consideration and try to find out. Now let us go step by step. So this is a graph which shows the conduction band edge here. This is the energy, and this is your conduction band edge. This is your valence band edge. This is my Fermi level. So Fermi level is a place, we will not discuss at this stage the intrinsic Fermi level, and intrinsic Fermi level EFI is generally equals to EC plus EV by 2, or half of the function. This is known as the forbidden energy gap, and half of it is EFI, which is the intrinsic Fermi level, right, and it is also referred to as a mid gap energy. Now I have already drawn the value of GCE and GVE. GC is the conduction band density of states and GV is the valence band. Now what has happened is my Fermi level is above the mid gap energy and very close to the conduction band, which means that the probability of finding electron in the conduction band will be larger, and that is shown by this graph here, this blue colored graph. This is the number of electrons per unit volume per unit area. This is always large, you see, as compared to the number of holes. So if you plot this graph, this is F of E, which is being plotted. This dot and dashed curve which you see, F of E. Now you see it is mostly included within the conduction band and goes to a very low value near the valence band. So if you multiply F of E with respect to the conduction, this will be very small quantity which you see here, and this will be very large quantity. And this tells me one important point, which I will just show it to you, that the number of electrons equilibrium is given by GC of E multiplied by Fe of E. Even if this is constant for valence band and conduction band, if this is larger for conduction band, the number of electrons will be much larger as compared to the number of holes, at T equals to 0 Kelvin, right. That is what is shown at this graph or this position here, that the number of electrons are much larger, the area under the curve is very much large, and therefore we will get this thing. So now let us do one thing, theoretically you can do it yourself also, that EF, bring it closer to EFI. When you bring it closer to EFI, then the number of electrons will be exactly equals to the number of holes. Why? Because the electrons which were bound state in the valence band at higher temperature will, or at even other temperatures, will be jumping the forbidden energy gap and going to the conduction band. So any empty state at the valence band will be corresponding to a filled state in the conduction band. That is only true when the Fermi level is closer to EFI. So when EF equals to EFI, you will have this symmetricity available. But if EF is much closer to the conduction band, you will have much larger number of electrons, and if it is much closer to the valence band, you will have larger number of holes. Now let me come to the thermal equilibrium concentration, and we define the concentration of electron N0 to be equals to GC of E of Fe into E. So similarly, P0 will be given as integral of GV of E into F of E dE. So that is also there, and this is from EC to, let me say, infinity, and then this is from EV to infinity back, right, and you can find the value of P0 here. Now if you apply the Boltzmann approximation, which is F of E is equal to this much, and this is basically nothing but exponential minus E of EF by KT, this formula, then if you substitute F of E into G of E formula, I get N0 to be equals to EC2 is equals to 4 pi 2 mn star h cube 3 to the power 2 exponential so value, right. Therefore, if capital E is much larger than EC, right, E is much larger than EC, the number of electrons will obviously be larger, because you have no more number of states available to you. At E equals to EF, again this goes to 0, this whole thing converts to 1, and you are coming back to the original state of N0 equals to P0, clear. So this is what is known as the Fermi-Dirac distribution for electrons, right. Now this expression can be simplified into form of this expression, where N0 is given as 2 something to the power mn star KT by h square exponential EC minus EV, because E will get cancelled out, I will get EC minus EF. Now this quantity is referred to as this quantity NC, right. NC is given by this value. NC is a effective number of states available, and this is given by for a fixed temperature, the value of NC is also constant. So what we do, the final expression for the thermal concentration of electron N0 can be written as NC equals to exponential minus EC minus EF by KT so on and so forth. So now you see, as you make EC equals to EF, right, EC equals to EF, then we get N0 equals to NC. And you know what will happen when EC becomes much larger as compared to EF, they are very far apart. Then what will happen, this quantity will go on reducing because it is minus negative sign here, right, and therefore this quantity will go on and N0 will go on reducing. So when EC and EF are closer to each other, so when EC is approximately equals to EF, N naught is equals to NC, the maximum value, and when EC and EF they are far apart from each other, or EC much larger than EF, when the gap between EC and EF becomes larger, you end up having almost a zero number of free energy electrons available to us, and that is explainable by this quantity over this particular point. We can write for holes also. In this case, P0 is given as NV exponential is just symmetrical with respect to each other, minus this will be EF minus EV divided by KT. All the explanation which is holding for electron generally will hold for holes also, right, where NV will be given as 2 into 2 pi MP star KT by h square to the power 3 by 2, correct. So this is the overall understanding which we have for NC and NV. Please understand, NC and NV, which is effective number of electrons available to us, will be given by Mn star and T. So if you assume the T value is same, generally the effective mass of holes are much larger as compared to that of electrons. So typically NV will be larger as compared to NC for all the cases, and therefore perfect symmetricity of NC and NV is not available in this case. Let us come to charge neutrality, right, and this is very important from the point of view of cryogenics as well as basic device understanding. We will look into the charge neutrality aspect. Now what is charge neutrality? It states that the total number of charges, effective number of charges will be always constant, right, and if you do not do a doping, you do not do anything else, if any electron is created, a hole will be also created at exactly the same instant of time, right. Now let us look at the left hand side diagram. Looks complicated, it is relatively easy if you understand. So I am saying the total number of hole concentration free holes is P0 and the total number of electron concentration is N0. Now you can have thermal electrons being available. Why? Because if there is a temperature increase, if the energy is larger than the band gap, electron hole pairs will be generated. Again the number of electrons will be exactly equals to the number of holes. That is shown here and here, right, and they will be perfectly in consonance or neutral with respect to each other. Now if you put a donor species into semiconductor, what they will do is that they will donate one of their electrons to the conduction band, because its level is very close to the conduction band. So even at 300 Kelvin, a donor species, for example a phosphorus group 5 element, will donate some of its electron to the conduction band, itself becoming positive. You see this one, and this becomes positive. Again the net number of charges is again remaining constant. Same thing happens for acceptor ion. So if this is an acceptor ion, it accepts electron, converting this to positive charges. So you see this and this is explained. Then there will be some ionized donors, right. Ionized donors means who have donated the electrons and themselves becomes positive charge, and there will be exactly the same number of negative diionized charge. So if you look at any semiconductor, forget about the word compensated at this stage, look at any semiconductor, the effective number of free electrons is N0, effective number of free holes are P0, effective number of ionized acceptors will be given by Na minus Pa, and effective number of ionized donors are given by Nd minus Nd, right. So if you look very carefully, N0 equals to P0 consists of all free charges, and Na minus Pa is the effective value of the ionized acceptors, right. So these are fixed charges, and Nd minus Na is also a fixed charge, this is also a fixed charge, this is a mobile charge, and this is also a mobile charge. So what you see from this diagram is the number of mobile charges and fixed charges, if you add together, they always become equal to each other. However, if you want to generate an N type, you will have to make your Nd much larger than Na, then this becomes much larger than this, and therefore compensation is uncompensated. Similarly, if you want to make it P type, Nd will be Na P type, your acceptor ion concentration should be much. So this is a mistake here. This should be, both are same. This should be Nd should be less than Na. So please make a correction. Nd, so Na must be much larger. Acceptor ion concentration should be much larger than a donor ion concentration, because you will be accepting electrons, right, converting them into positive charges, and these are free positive ions which are there. Please keep in mind all this discussion is the fact that the donor species and the acceptor species are hardly few kT energy level different from the value of EC and EV. If they are very far from that EC and EV, they will as well not be able to donate any of the species. So that is the reason I am assuming that they are very close to each other. So therefore, let us look at the thermal equilibrium concentration. We say that if we assume complete ionization, which means that what is the meaning complete ionization? That 100% of the donor species have been ionized. Then what we get from all this discussion is that N0 plus Na equals to P0 plus Nd, where P0 is equals to Ni square by No, because N0 P0 is always equals to Ni square, right. And from there, if you solve it, I will not go into details, I get N0 to be equals to this, right. Now interestingly, and this will be true also, if Na equals to Nd, then you see this vanishes, this quantity vanishes, and you are left with Ni, root square of Ni. Root square of Ni becomes N0 equals to Ni, which means that if you take a semiconductor, right, an intrinsic semiconductor, say silicon semiconductor, and then you dope with say 100 atoms of donor species, and then again you dope with 100 atom of acceptor species, then effectively it converts into an intrinsic semiconductor, and therefore N0 becomes equals to Ni. Ni is intrinsic carrier concentration of the electron of the order of 10 to the power 10 per centimeter cube, which means that whenever there is a thermal equilibrium for a compensated semiconductor, you will never get excess of charge carriers. For an uncompensated one, you will get a charge carrier acceptance, right, and that will be there always. So let me show you a numerical problem. What it says is that you need to calculate the intrinsic carrier concentration for silicon at T equals to 250 Kelvin and 400 Kelvin. So I am not putting at 300 Kelvin. 300 Kelvin values of Nc and Nv are given to you, but what we need to find out is what is the intrinsic carrier concentration at 250 and 400 Kelvin, and the Nc Nv value is given as this, right, is given at 300 Kelvin is given as this and this respectively, and both Nc and Nv vary to T to the power 3 by 2. We have already seen that point. If we assume that band gap energy is 1.12 and we assume that it does not vary with temperature, but strictly that is not the case, assuming at this stage it does not vary, then you are told to find out the intrinsic carrier concentration. So we know that if we look at the previous equation here, right, Ni is square, right, this is N0. So N0 into P0 will be equals to Ni square. Remember, from there I can get this expression that Ni square equals to multiply of that to the power 3, 250 by 300 exponential this quantity, and you get this where Ni comes out to be this. Now quite interesting, you just see the numerical solution is one way of looking at it, but conceptually look at the fact. Conceptually, if you look at Ni at 300 Kelvin, it is of the order of 10 to the power 10. So what has happened is, as you lower the temperature, the intrinsic carrier concentration also drastically reduces to a value equals to 10 to the power 7. So there is a 3 order difference in the intrinsic carrier concentration when you move from 300 to 250 Kelvin. This is for 400 Kelvin, and in the 400 Kelvin you see you have a 2 order increase in the intrinsic carrier concentration, which means that if the calculations are done at a higher or lower temperature, the intrinsic carrier concentration itself would change, right, and therefore though the equilibrium statistics will still remain the same, but the intrinsic carrier concentration will change. So just to give you an idea about what we did in this whole lecture, because now we will be shifting gears from quantum mechanics density of states concept to basic MOSFETs, which I will take up in just now with you. But let us recapitulate what we did in our class. So we did first of all understood the meaning of conduction band, right, and the valence band. Then we looked into density of states, right, and from density of states we went to Fermi-Dirac probability and Fermi-Dirac distribution. We saw that at T equals to 0 Kelvin, my f of E, right, is equals to 1 by 2, stating that all states below EF is filled and all states above EF is empty. These things we have learned. Then we took this concept and tried to find out the value of N0 and P0 by integrating what? By integrating G with Fermi, G with Fermi. We integrated it, and after that we found the value of N0 P0. Now in all probability at equilibrium, N0 P0 will be always equals to Ni square, right? It will always be equals to Ni square. But however, Ni is again function of temperature, and we saw that at lower temperature Ni value drops down, at higher temperature Ni value actually goes up. And one important point to be kept in mind is that the value of Nc Nv are also not symmetrical, because they have an Mn star and Mp star concept. So Mp star will be always larger than Mn star, which means that the effective hole mass is always larger than the effective electron mass, and that is the reason you will have this sort of this thing change, right? And that is what we have learned this thing. In our next lecture, we will be actually working with MOSFETs. This is where we finish our quantum mechanics required for cryogenics. That is enough. We will revisit as and when required the basic concepts, so make it clear. A good book to look into is obviously Niemann, but very good book which I found to be very interesting is Pierre. I am not very sure about the spelling. This is a very old book, 1965-62, but gives you a very concept idea. Then we have Niemann, right, which is Donald Niemann. So if you are at UG level studying this course, these are the two books to go by, and those who are into PG level, you can add another book to it, and that is Streetman. You can actually look, even Streetman UG people can also look. You can look at Streetman, you can look at Cividis for MOSFET, right? And I will name some books later on for cryogenics as well, right? So this is that you know where to approach these problems. I will share with you also some research papers, those who are interested to work in this domain for your master's, PhD or higher studies, or just for learning purposes, just the fun of it, I will be sharing it. So with this, let me finish this talk, and we will meet next time with MOSFET.